This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 9, Pumps and Compressors as Machines. Lesson 1, put the pump on its system. Here we look at the machine itself, the affinity laws that scale a pump when you change its speed, the net positive suction head margin that keeps it out of cavitation, and the work and isentropic efficiency of a compressor. For pump fundamentals, the thermal fluids course Week 4 is the primer. Concept 1. The pump as a machine. Change the speed or trim the impeller, and the whole curve scales by powers of the ratio. Flow with the first power, head with the square, brake power with the cube. Swap N for D to trim the impeller. A denser fluid changes only the brake power, scaling with specific gravity, and the absolute brake power itself is flow times specific weight times head over efficiency. Concept 2. Net positive suction head and cavitation. At the suction, the fluid has a net positive suction head available, the pressure head plus the static suction head minus the vapor pressure head minus the friction loss. The pump's curve gives the head it requires. Cavitation is simply when available drops below required. It's the sign of the margin, not a separate formula. Concept 3. The compressor as a machine. Its shaft work follows the enthalpy rise, and for an ideal gas, that's specific heat times the temperature rise. The handbook prints it with a minus sign, a workout convention. So for compression, the number comes out negative, meaning work flows in. Report the magnitude as the driver power. For refrigerant enthalpies, cross-reference Week 3. Concept 4. Isentropic efficiency. A real compressor exits hotter than an ideal one at the same pressure ratio, so it takes more work. Efficiency is the ideal temperature rise over the actual, and it's always below 1. A turbine flips the ratio, because a real turbine delivers less than ideal. Here's the picture on one flow axis. Up top, the falling pump head curve crosses the rising system curve at the operating point, the flow the pump actually delivers. Down below, two more curves, the head available at the suction and the head the pump requires. Their gap at the operating flow is the cavitation margin. Positive is safe, close it, and the pump cavitates. Solve. Speed 1 pump up 20% from 1750 to 2100 RPM, a ratio of 1.2. Flow takes the first power and goes to 600 GPM. Head takes the square to 144 feet. Brake power takes the cube to about 35 horsepower. 20% more speed, but 73% more power. That cube is why slowing a pump saves so much. Solve. Check the suction. Add the atmospheric head and the static suction head. Then subtract the vapor pressure head and the friction. With a suction lift, the static term is negative, and available comes to 20 feet. The pump requires 14, so the margin is 6 feet. Positive. No cavitation. Watch that lift sign. It makes the available head smaller. Traps. 1. The affinity exponents, flow first power, head square, power cube. Swapping them is the classic miss, and specific gravity scales power only. 2. Net positive suction head is a margin. Available must exceed required. Compare the two, not the discharge pressure. 3. A hotter or more volatile fluid raises the vapor pressure head and eats the margin, and so does more lift or friction. 4. The printed compressor work is negative, so take its magnitude, and isentropic efficiency is ideal over actual. Quick recall. Affinity laws for a speed change. Flow first power, head square, brake power tube. Specific gravity scales power only. Absolute pump power is flow times specific weight times head over efficiency. Available suction head is pressure plus static minus vapor pressure and friction. Cavitation when it falls below required. Compressor work follows the enthalpy rise, and isentropic efficiency stays below 1. Lesson 1, put the pump on its system. Here it's the machine, and the affinity laws mirror the fan laws you already know. Next up, Lesson 10, exam strategy and worked equipment problems. We'll drill the signature traps side by side, the 15,000 tower ton versus the 12,000 refrigeration ton. LMTD versus effectiveness NTU method choice. The affinity exponents, and the NPSH margin sign, all on mixed equipment problems. Everything's at PEPrepEngine.com. Cheat sheet, work solutions, and a quiz. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com. Link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.